Hello and welcome back to Calc 3. We're going to talk about spherical coordinates today, but first I want to start with a little recommendation. So I'm going to give little recommendations every day moving forward in class of something to go check out if you want to do something other than calculus or just to relax. I think it's great in times like these to make sure you're unwinding and connecting to other people socially. And I think exchanging music recommendations is one of my favorite ways to do that. So my recommendation today is this album by the German composer Hauschka. I don't know how to pronounce that name, I'm sorry. The album's called A Different Forest, and Hauschka's a pianist, and he improvises an amazing album that really gives you the sense of wandering around a kind of misty, moss-filled forest. It's very peaceful, and if you've been kind of anxious recently, maybe this music, turning it on while you're studying, will help things out. So, let's talk about spherical coordinates. So, I'm gonna start by just giving this slogan, which is that I've used spherical coordinates as polar and polar. So think of it as polar in the xy plane and polar in the rz plane from cylindrical coordinates. So let's unpack that. So if we have a point floating somewhere up here in space, so I'm going to draw it in blue, how we find what the spherical coordinates are for that point is we project it down into the xy plane, and in the xy plane, that point we're going to put in polar coordinates. So in order to do that, in the xy plane, we're going to find an angle theta and a little interval r that would tell us its coordinates in the xy plane. So in just the xy plane, we've got this point. These are the x, y coordinates of our point, which starts as x, y, z. And we are finding r, and we're finding theta. And so we can use our r cosine theta and r sine theta conversions to get x and y, or go backwards to figure out what r and theta are. So put x and y in polar. Then you're going to put r and z in polar. And so in this left diagram, we've got this r pointing out and this distance going up. That's our z component. And so if I draw that over in the RZ plane on the right, I've got R down here, and then I'm going to go up a bunch to get, here's my Z distance vertically, and here's my actual point. And so this is supposed to be like the RZ plane is this slice at the angle theta from the x-axis. So along that plane, I'm trying to describe what's going on. And the way we do spherical coordinates is we do polar here, but you're going to do polar from the z axis, from the z-axis. So what that means is rather than using, kind of r and theta the way we wrote it in that place, I'm going to draw a triangle as you'd expect, but this angle here, that's going to be our new polar angle. We are already used theta, so we're going to call this one phi. And this length we're going to call rho. Rho is Greek letter r, so you should think of it as radius, but we're not going to use lowercase r because that's reserved for cylindrical coordinates. So we're using Greek rho. And those are our coordinates of this point. So in Cartesian, you write it as x, y, z. And in spherical, you're going to write it as rho, theta, phi. And let me draw what I just did in this picture also over here in the xyz plane. So what we did was we found this length right there, and that length of it is rho. It's the distance from the origin, you'll notice. So it's actually our radius from the origin. And, I guess, in the plane, because we're in this plane, I'm projecting back, this angle here is phi. Okay. So that's kind of abstract. Let's go look at what the expressions this gives us. So let's just summarize them over here on the right, and then we'll kind of connect them up to what we know so far. So x and y, right here in the middle, we know x should be r cosine theta, and y should be r sine theta. Those are not new formulas to know because that's just cylindrical coordinates. That's just polar coordinates. That's just easy to remember. Now the new step is to remember these new polar coordinates. So you'll notice r is this top length and z is this left length. And because we're doing polar with respect to phi in the RZ plane, r is now being re-expressed as rho sine phi, because it's the opposite, and z is rho cosine phi. And I'm telling you right now, if you remember these two facts, you've basically got all of all of spherical coordinates down. So remember polar in xy, remember polar in zr, and then you've got everything else. So if you follow these key formulas over here on the right, if you remember x is r cosine theta, in spherical coordinates, you don't want that r to be there. You want everything to be in rho, phi, or theta. And so we'll replace r by rho sine phi to get r cos theta. And y is going to be rho sine phi, which is another r, sine theta. It's convenient to use this substitution. R is rho sine phi. You'll use it when you're going back and forth between spherical and cylindrical coordinates and kind of when you're interpolating them. Z is now just rho cosine phi. There's no additional theta component in there. It didn't matter. From polar coordinates, we know r is x squared plus y squared. So that's this expression here. That's nice. And so now rho squared has to be r squared plus z squared from polar in the RZ plane. And so you can expand that and realize that rho squared is just x squared plus y squared plus z squared. In other words, rho is really the distance of the point from the origin. I'm going to write that down just to be clear. Great. Now we have this new volume element, and if you just look at the bottom line, sometimes it's hard to, I find it hard to memorize that and understand why it matters. But you should think of this just as taking the Cartesian one, and in order to get cylindrical, what we did is we converted the x and y's to polar coordinates. So I did this here. I took the dx and dy, and I turned them into r, dr, d theta, the green text there. So if you remember to do polar for x and y, now you have the cylindrical volume form. If you also want to get the spherical volume form, we need to take dz and dr and turn them into polar. And so the polar coordinate form for that is going to be rho for the radius in the polar coordinates and d phi for the angle in those polar coordinates. So I got rho, d phi. That r I'm rewriting just as rho sine phi because I want everything in this spherical expression to be in terms of my three variables, rho, phi, and theta. And then the d theta stays there. And so people prefer writing this as, and often memorize it as dv equals rho squared sine phi d rho d phi d theta. And it's not important to know any other derivation of this, but it is important to have all of these three formulas really secure in your brain. And if you remember polar, you're going to remember them all. Okay, so let's look at a couple ways to graph things in these different coordinate systems. So let me zoom out a little bit. We're going to do some basic graphs. Let's first do the spherical ones. So I feel like these are a little rendering a little weird for me. Yeah, I'm not really sure what's going on there, but we'll work with it. So rho equals 2. This is going to happen when you're looking at all the points whose distance from the origin is 2. That is just a sphere. So that's a sphere whose radius from the origin is 2. And then if I also draw my x, y, z coordinate axes in here, they might look something like this. So let's label these. This is going to be x, this will be y, and here's z going up. And so this is a sphere. So if rho is constant, you're actually just looking at a graph of a sphere. If phi is constant, at pi over 4, I am now remembering that I should talk about these things up here. So for cylindrical coordinates and for spherical coordinates, we do some restrictions on the standard restrictions on the variables. So for cylindrical coordinates, r can be bigger than anything bigger than 0. You can allow it to be negative, but for these examples, we're going to think about it being positive exclusively. So points are uniquely determined. And theta is in between 0 and 2 pi, and z can be anything. For spherical coordinates, there's a little unusual discrepancy, which is that phi is only between 0 and pi. And to think about that, we're going to think about that, unpack that in this little example. So the key here is if phi is pi over 4, then I'm not really restricting my x and y coordinates. I'm only restricting the z relationship. And so the graph you're going to get is a cone. So let's draw a little cone, and I'm going to draw my z-axis going up. So here's x, here's y. So why is it a cone? Is because the only stipulation here is that the points that you care about, the angle that they have with the positive z-axis, phi, has to be pi over 4, right? And so pi over 4 is halfway up. It's a line of slope 1 in the zr plane. So that's like a 45-degree angle in there, in that cone, in half of the cone, right? So the total angle of the cone would be a right angle, but yeah, this is half of it. And so you have this positive upward-facing cone. If phi is, let's say, getting closer to pi, so 3 pi over 4, then this angle that you'd have would have to extend all the way, here's pi over 2, would have to go all the way to 3 pi over 4. And then you'd want to look at the negative z-axis and realize that what you have is a cone whose angle with the negative z-axis is pi over 4, and with the positive z-axis is 3 pi over 4. And so as you vary phi, you're going from really narrow cones around the positive z-axis to, as it kind of opens up, all of a sudden it becomes the xy plane at phi equals pi. And that's somehow a cone where you've like completely opened it up to be flat, but then you start flipping the cone around to be these green cones on the negative side that get narrower and narrower around the negative z-axis. But we're not going to allow phi to go any bigger than pi or any smaller than 0, because those would be cones that, are already defined as we swept around. And so these other restrictions on the spherical coordinate system should make sense. Phi can be, or theta can be anywhere between 0 and 2 pi, and rho can be anything positive. And again, we're going to kind of restrict to the positive ones. So now for theta, this turns out to be totally the same as what it was before. So if we have our x, y, and z axes, if you've picked some, that's a pretty bad picture of, x. Yeah, so if you've picked pi over 4 to be your angle, you take a plane. Let's draw it in blue. You take a plane going through this exact line in the xy plane and going vertically up along the z-axis. If rho is strictly bigger than or equal to 0, you're not going to get the plane in the negative direction. So it won't be pointing backwards from the angle pi over 4, so it's not going in that direction, in a sense. So, yeah. So it's just kind of like half of the plane pointing in this direction that I've drawn. So in this direction. Okay, so for cylindrical coordinates, we did these last time, but let's just quickly review. So if r equals 2, what we're graphing is in fact a cylinder whose radius is 2. And it's a cylinder around the z-axis. If theta equals pi over 4, we again get this same blue diagonal plane that we got in the x and y case. So here's the line that they run on, and here's the pi over 4 angle, so it's the same as up above in spherical. And if z equals 2, we just have a plane going through. We got a plane going through z equals 2. So we got a plane here, we got a plane, or half of a plane, and this is a cone. And here's a cylinder. And finally, for x equals 2, y equals 2, and z equals 2 in Cartesian coordinates, what we're left with is just planes all the way around. So there are the 3 planes. I just drew them quickly for you. That's what they look like. Let's move on to some examples.